Hi everyone, my name is Kimal Anujam, and in this very short lesson, we will be reviewing for the final examination coming up on Wednesday. So I decided to do this because I wanted you to go through this practice exam with me wherever you are at your own schedule, but it is very important that you do this before you come into the examination. Now, this exercise is the practice exam for the final exam. At the same time, it is also homework number 3. Now, all you are required to do is listen to this lecture, write down the solutions in detail as I have written the solutions down. Then you will present this practice exam to me on the day of your exam, which is coming up on Wednesday. Now, this will be homework 3. Also, if you have 100% on this, you will have an opportunity to earn extra credit as well for the class. So this is really a good opportunity for you to catch up if you need to catch up. And also, I wanted to do this so that you could have a less pressured way of reviewing for the finals. Now, the questions in this practice exams are meant for you to practice, and if you are able to do all the questions in this practice exams, you should do very well in the final examination. Now, the questions in the final exam are totally different from the questions in this practice exam. So do not concentrate your efforts in trying to memorize the answers, but focus on understanding the principles behind each problem. I'm going to go through the problems step by step to ensure your complete understanding. Now, secondly, the instructions for the exams are simple. This exam is meant for you to demonstrate that you've understood the physics behind every problem. Now, in order for you to show that you've understood the physics behind every problem, you must show step by step how you get to your solution. Which means that if you just write down a correct answer without demonstrating or showing how you got there, you will earn 0 credit. Also, it is important for your work to be very neat and very clean as you write down during the examination. Now, it is okay for you to make mistakes, but when you do not just erase everything. Simply strike a line through your work. You may earn extra credit even though you discarded the work. So do not erase completely or try to put out everything. I also highly recommend that you write your name on every exam sheet, especially because some of you often take off the clips, and if one of the loose papers fall apart, I may not be able to identify which student. So write your name on every sheet in the examination. Understand that during the exams, if you have any questions, I recommend that you ask. But not every question that you will ask me, I will be able to answer the questions, but it is recommended. I do recommend that you do ask questions. Now, apart from that, sit tight and enjoy this particular learning session with me. So the very first question is in static equilibrium, which means that the very first question in the exam is going to be in static equilibrium. So what do we mean when we say that an object is in static equilibrium? An object in static equilibrium must fulfill 2 conditions. 1, the net force acting on the object must be equal to 0. This means that the object will not accelerate. Now, what this means is that the sum of forces along the x direction must be equal to 0, and the sum of forces along the y direction will also be equal to 0. This is the first condition of equilibrium. The first condition of equilibrium. Now, the second condition of equilibrium is that the sum of torques around any point must be equal to 0, which means that the angular acceleration will be equal to 0 as well. Now, if these two conditions are fulfilled, we say that the object is in static equilibrium. We say that the object is in static equilibrium. So the question requires us to calculate the mass m. We will start the question by looking at the torques about 1 and then go to 2 and then 3. So let's lock and roll. So the torque about 1, we know that the summation of tau 1 will be equal to 5 grams multiplied by 4 centimeters minus m1 multiplied by 2 centimeters. All of these will be equal to 0. So what this means is that 5 grams multiplied by 4 centimeters will be equal to m1 multiplied by 2 centimeters. So m1 will be equal to 5 grams multiplied by 4 centimeters divided by 2 centimeters. If you notice, I write everything including the units. So you should also keep in mind that when you express your work the way I'm expressing mine, it's very easy for you to track down your units. So your answer will be 10 grams. So M1 will be 10 grams. Now, this right here is 1 point, 1 point, and 1 point. So in total, you've already earned 3 points. So the next part is to calculate the mass M2. So if we sum the torques about 2, we will have M1 plus 5 grams multiplied by 1 centimeters minus M2 5 centimeters. All of these will be equal to 0. But remember that M1 is 10 grams. So this means that 10 grams plus 5 grams multiplied by 1 centimeters will be equal to M2 multiplied by 5 centimeters. In other words, M2 will be equal to 15 grams multiplied by 1 centimeters divided by 5 centimeters. Now, if you notice, the centimeters will take care of centimeters. 5 here into 15, 3. And that means that M2 will be equal to 3 grams. So we've calculated M2 to be equal to 3 grams. This is 1 point, 2 points, 3 points. So in total, we already have 6 points. The next, we will now look at the point. We're now going to take the talks about the point 3. So we have the summation of tau 3 will be equal to big M multiplied by 4 centimeters minus M1 plus 5 grams plus M2. All of this multiplied by 8 centimeters will be equal to 0. So if we sum up everything, we will have, this would mean that M multiplied by 4 centimeters minus M1. M1 is 10 grams plus 5 grams plus 3 grams multiplied by 8 centimeters. This will be equal to 0. This would mean that M multiplied by 4 centimeters is equal to 15 plus 3, that's 18. So this is 18 grams multiplied by 8 centimeters. If we divide both sides by 4 centimeters, we will have M equal to 18 grams, 8 centimeters divided by 4 centimeters. The centimeters cancels off with centimeters. 4 here, 1, 4 into 8, 2. This would mean that big M is equal to 18 multiplied by 2. And 18 multiplied by 2 is going to be 36 grams. 36 grams. So this is 1 point. This is 1 point. This is another point. And this is another point, giving a total of 10 points over 10. So if you follow this simple schematic, or this simple procedure, you are on your way to 10 points on problem 1. So let's move on to the second problem. So question number 2. A container has a vertical tube whose inner radius is 24 millimeters connected to it at its side. This tube right here. An unknown liquid reaches level A in the container and level B in the tube. So this is level B in the tube and this is A in the container. Level A being 5 meters higher than level B. So this distance is 5 centimeters higher. The liquid supports a 20 centimeter high column of oil between B and C, whose density is 570 kilograms per meter cube. We are asked to determine the mass of the oil in grams. I can also ask you to calculate the gauge pressure at point B, piece of B, or I can ask you to determine the density of the unknown liquid inside the container. So these are all possible questions that I can ask you to calculate during the exam. So it is important that you pay close attention to this problem, because just this single problem, a variety of questions can be generated from it. So let's move on. By definition, density is given by the mass divided by volume. This would mean that the mass is equal to density multiplied by volume. But this is a cylinder. What is the volume of a cylinder? The volume of a cylinder is given by the area, which is pi radius squared multiplied by h. Fortunately for us, the radius is given. We know the height. And so the rest of the problem right now is just to plug in the values. So this will be equal to the density of the oil is 570 kilograms per meter cube. Don't forget your units. Pi is a constant, 3.14. The radius is given to be 24 millimeters, which is the same as 2.4 times 10 to the power negative 3 meters. And all of this is squared. The height of the tube is 20 centimeters, and this is just 0.2 meters. If we calculate all of this, we will end up with a value of about 0.21 kilograms. 0.21 kilograms. So this is the mass of the oil in the tube. I can also ask you to determine I could have asked you to determine the gauge pressure at point B. In other words, I could have asked you to calculate the pressure at B. So the question is, how would you determine the pressure at B? In order for you to determine the pressure at B, you will need to apply the Bernoulli's principle. We know that the pressure at B, keep in mind that generally P is equal to P naught plus rho G H. So the pressure at B PB is equal to P atmospheric plus rho of the unknown liquid G H1. Similarly, PB with respect to the R is equal to P atmospheric plus rho R, which you know, GH2. If you combine these two equations, you will have the atmospheric pressure plus the rho unknown liquid multiplied by the acceleration due to gravity, H1, equal to P atmospheric pressure plus rho R, GH2. You clearly see that these can cancel out each other. And if you sum this up, you will end up with the density of R equal to, the density of the unknown liquid equal to the density of R, GH2, divided by GH1. The G's can cancel each other, and this will be equal to the density of R multiplied by H2 divided by H1. In which case, the density of the unknown liquid is equal to the density of R, which is 570 kilograms per meter cubed, divided by H2, which is 20 centimeters, divided by H1, which is 5 centimeters. All of this will be equal to 2,280 kilograms per meter cube. This is the density of the unknown liquid. This gives us the density of the unknown liquid. Now, to calculate the pressure of the ore, we can use the fact that PB is equal to P atmospheric plus the density of the unknown liquid, GH1, which will be equal to the atmospheric pressure. This is 101,325 pascals plus the density. We could use any one of these, either this or this, and the answers will still be the same. So I'm going to use that for R plus 5 570 kilograms per meter cubed multiplied by 10 meters per second squared multiplied by 0.2 meters. And if you calculate, your answer will come out to be 102,465 pascals. So this gives you the pressure at point B. So let's move on to the third question, which is actually on calculating the specific heat capacity. So the question is, how many grams of ice at minus 23 degrees Celsius must be added to 176 grams of water that is initially at a temperature of 69 degrees Celsius to produce water at a final temperature of 8 degrees Celsius? Assume that no heat is lost to the surroundings and that the container has negligible mass. The specific heat of liquid water is given, that of ice is given, as well as the latent heat of fusion and vaporization of water is also given. So how do we approach this problem? Now, initially, we have a container with water. Then we have ice. So the ice is at a temperature of minus 23 degrees Celsius. And the water is at an initial temperature of 69 degrees Celsius. Then what do? We add the ice to water. When we add the ice to water, it floats. But what do we expect? The ice will eventually melt. When the ice will melt, the water and the ice will settle down at a particular temperature. Let's call that temperature T. And in this problem, T is equal to 8 degrees Celsius. So the question is, we need to calculate the amount of ice that will be added to water at 69 degrees Celsius such that the final temperature will be 8 degrees Celsius. Now, here is the deal. When we add ice to water, the ice gains heat and the water loses heat. So we know that the heat lost by water must be equal to the heat gained by ice. Must be equal to the heat gained by ice. Now, the question that I will need to answer is, when ice gains heat, what happens? So let's first of all calculate the amount of heat lost by water. The heat lost by water is equal to the mass of water, the specific heat capacity of water, times the temperature change of water. This is the same as the mass of water, the specific heat of water, the temperature change of water is going to be equal to T minus T naught. So if we put in the values, The mass of water is 0.176 kilograms. The specific heat of water is given to be 4190 joules per kilograms per degree Celsius, multiplied by the change in temperature. This is going to be 69 degrees Celsius minus 8 degrees Celsius. If you calculate your answer, this is actually going to be 44983.84 joules. This is the heat loss by water. Now, the important question that you need to ask yourself is, where does this heat go to? The heat lost by water is equal to the heat gained by ice. But when ice gains heat, what does it do? The heat gained by ice is equal to the heat required by ice to raise its temperature to 0 degrees, which is given by M ice, C ice, multiplied by the change in temperature, plus the heat required to melt ice at 0 degrees, which is the latent heat of fusion. So this is going to be M ice multiplied by LF, plus when the ice becomes water, the heat required to heat the water at 0 degrees to raise its temperature to the final temperature 8 degrees. So this is going to be M ice, C ice, multiplied by the change in temperature T final. So if we do this, remember that the initial change in temperature is to raise the temperature from minus 23 degrees Celsius to 0 degrees Celsius. So this is going to be equal to 23 degrees Celsius. And delta T final is equal to 0.8 degrees Celsius minus 0 degrees Celsius. Minus 0 degrees Celsius. This is going to be 8 degrees Celsius. So if we put in all the values, we will have the heat gained by ice will be equal to M ice multiplied by the specific heat of ice, which is equal to 2000 joules per kilograms per Kelvin or per degree Celsius, multiplied by 23 degrees Celsius, plus M ice multiplied by the latent heat of fusion for ice, which is equal to 334. It's actually given in the problems. 334 times 10 to the 3 joules per kilograms, plus M ice multiplied by the specific heat capacity of water, which is 4190 joules per kilograms per degree Celsius, multiplied by the change in temperature, which is 8 degrees Celsius. Now, if we add up all of these quantities, we will end up with 413 1.352 m ice. This is the heat gained by ice, and we know that by the law of conservation of energy, the heat gained by ice is equal to the heat lost by water. In other words, QW is equal to Q ice. This would mean that 44983.84 is equal to 41352 m ice. And if you simplify, m ice will be equal to 44983.84 divided by 41352 kilograms. If you work this out, this will be about 108 grams. It will be about 108 grams, and that will be your answer. I would recommend that you should pay close attention to this problem. Now, to recap the main points, if you put a block of ice in water, the water will lose heat energy and the ice will gain heat energy. Now, the heat lost by water is equal to the mass of water times the specific heat capacity of water times the temperature change of water. The heat gained by ice does three things. One, it melts the ice. Remember that for ice to melt, its temperature needs to rise from whatever temperature it is to 0 degrees. And at 0 degrees, heat is going to be added to the system and the temperature will not change. We call this heat latent heat. When the ice is melted, then it continues to absorb heat energy until its temperature rises up to the temperature at thermal equilibrium. So it's important you keep this in mind. Now the next problem is actually a problem in gas laws. So the question is, the figure shows a 2.6 gram of ideal helium gas that undergoes the process 1 to 3, 1, 2, and 3, and we are required to determine the value of V3. We are required to determine the value of V3. Now, first of all, 1 to 2 occurs at a constant volume, so this is an isochoric process. And in an isochoric process, the change in volume is 0, which means that the work done by the gas is 0. Now the process 3 to 1 occurs at a constant pressure, so this is an isobaric process, which means that the pressure is constant. Now the work done by the gas is just going to be equal to P from 3 to 1 multiplied by V1 minus V3, this is the change in pressure. The heat exchange during this process is equal to Cp, the heat capacity at constant pressure, multiplied by T1 minus T3. It is worthwhile for you to remember that the change in internal energy is equal to Q plus W. This right here, my fellas, is the first law of thermodynamics. Now, the process 2 to 3 is isothermal. Isothermal implies that the temperature does not change, which means that T2 is equal to T3. And if T2 is equal to T3, it means that there is no change in the internal energy at during this particular process, in which case a heat added to the system is just going to be equal to the work done by the system. And the work done by the system, it's given by NR, the natural log of V2 over V1. Like I said in class, you will rarely use this, but I give it to you anyway because you need to know this. But the trick to solving this kind of problems is to always remember that the net work done by the system is simply the area enclosed by the graph. It could be a rectangle, it could be a square, it really doesn't matter. But in this case, how do we go about this? We know that the gas is ideal. We know the mass of gas, but we are required to calculate the volume V3. So let's take down some data. V1, we don't know that yet. V3, remember that V1 is equal to V2, and we don't know that yet. V3 is what we are looking for. Similarly, T1 is equal to T2, which is essentially equal, T2 is equal to T3 because 2,3 is an isothermal process, which is 5, 6, 7 degrees. T1 is equal to 37 degrees Celsius. In the same token, P2, we don't know, but we know that P1 is 2 atmosphere. So we have a couple of things that we need to do. First of all, given that the process 2 to 3 being isothermal implies that P2 V2 is equal to P3 V3. That's what that means. Now, the process 1 to 2 is isochoric, which means that the volume doesn't change. And if the volume doesn't change, P1 over T1 is equal to P2 over T2. Now, do we know P1? Yes, we know P1. Do we know T1? Yes, we know T1. Do we know T2? Yes, we know T2. So we can calculate P2. So this implies that P2 is equal to P1 multiplied by T2 divided by T1. This would mean that P2 is equal to P1, which is 2 atmospheres, T2, which is given by 6, 5, 7 degrees Celsius, all divided by T1, which is 37 degrees Celsius. All of this will be equal to 35.5 atmospheres. We know P2. We now know P2, but we don't know V2. How do we determine V2? If you recall, PV is equal to nRT, which implies that V is equal to nRT divided by P. So V1 is equal to nRT1 divided by P1. Similarly, this would mean that V1 is equal to N, and N is 2.6 divided by 4. Remember, it is helium, and the atomic mass of helium is 4. The number of moles is simply equal to mass divided by atomic mass. So multiply by R, and R is 8.31. This value is given to you. T1 is given 37 degrees Celsius plus 273 to convert the temperature from Celsius to Kelvins. And we have to do this because of the units for R, divided by the pressure P1, and P1 is 2 atmospheres. So this is 2.02 times 10 to the 5 pascals. Remember, 1 atmosphere is equivalent to about 1.02 times 10 to the 5 pascals. So if we calculate all of this, this will be equal to 8.3 times 10 to the minus 3 m cubed. In other words, we have calculated the volume V1, and we know that V1 is equal to V2. We know P2, we know P3. Do we know P3? So this means that V3 is equal to P2 V2 divided by P3. Remember that P3 is equal to P1. So this is P2 V2 divided by P1, and P2, which is calculated to be 35.5 atmospheres, V2, which is equal to V1, is 8.3 times 10 to the minus 3 meters cubed, all divided by P1, and P1 is given by 2 atmospheres, which is the same as 2.02 times 10 to the 5 pascals. If you sum all of this up, P3 will be equal to 25 liters. 25 liters. The next question.